All right, here we go. Algebra 2, Unit 1, Day 5, Take 24. Today we're going to describe and analyze the relationship between a function and its inverse. And so the key word for today is inverse. I thought I'd start us off with a dictionary definition today. Specifically, I want to look at the definition of inverse as a noun, something that is the opposite or reverse. And this is the term I like to focus on for what we do in math, the reverse of something else. And to talk about what that means in the context of the math that you're going to be doing, we're going to return to our metaphor of a function as a magic box. So remember, we originally, when we talked about functions, we said it's a magic box. There are rules that get applied. They turn inputs that go in into outputs that come out. So our function f on the left here, it takes an input of a, and it spits out b. Some rule applies, it turns a into b. What an inverse function is, it is the function that does the exact opposite or undoes what the original function does. This here we would say is the inverse of f. It's the inverse of f because if a b goes inside the inverse function, an a comes out and you're back to where you started. You'd all be all the way back here. So it undoes the work that the original f function did. Let's take a look to make that more concrete at a very famous inverse pair. On the left, we have the function f of x, and on the right, we have its inverse, the square root of x. Right? Those are opposites. 2 squared is 4, and the square root of 4 is 2, back to where you started. 3 squared is 9, square root of 9 is 3. 4 squared is 16, square root of 16 is 4. 5 squared is 25, square root of 25 is 5. If you were to do those back and forth, you'd be back to where you started. So here's an example. If we take f of 3, so we take this input of 3 and we put it into the function, we do 3 times itself, we get 9. Then if we take 9 and we make it the input to the inverse of f of x, we take that input, we put it as that 9, we make it the input to the inverse. The inverse applied to 9, the square root of 9, is 3. And we're back to where we started. So the second function undoes the first one. Okay? Key point here, a function's inverse is the function that would undo what the original function has done. It takes the outputs from the original function and turns them back into the inputs that gave us those outputs. I want you to see this in a couple more different contexts. First, here's one that you might recognize from Algebra 1, a domain and range mapping. So on the left, we have our domains. On the right, we have our ranges. And the arrows tell us how the function works. So we can see on the left, if you put a 1 into the f function, an x comes out. F of 2 is z. F of 3 is y. If we look on the right, we're undoing all of those relationships. So we take that x and we put it into the inverse functions domain, and out comes a 1. We take a y, we get back a 3. We put in a z, we get out a 2. So it's undoing everything that this original function has done. And the key thing to realize here, the domain of f of x is the same thing as the range of its inverse. Right? So domain, remember, is the inputs, and range is the outputs. So the inputs of f are the outputs of y, and vice versa. If we look at the range of f of x, that's this guy, it's the same thing as the domain of the inverse. So domain and range get swapped. And so, most commonly where we encounter domain and range is when we're looking at these graphs, right? So we've got a graph of a function. I'm going to label this function g of x. I'll do the first two, and then you'll do the second ones. G of x, I want you to pay very close attention to the notation here on the left. Right? On the notation here on the left, this should say g to the negative first, or g inverse. G of 1, okay, g of 1 means if a 1 goes into the function, what comes out? So I look for x of 1, and I can see that when a 1 goes in, a 6 comes out, because this is the point 1 comma 6. So g of 1 is 6. But if I asked, what was the inverse of g of negative 2? the inverse of g of negative 2. What this question is asking, and I'll write this out, what g of x equals negative 2? What could we put into the function and get out a negative 2? So I'm not looking for the x values this time. I'm looking for where does my original function have a y value of negative 2. And I have this point here, negative 3 comma negative 2. When you put a negative 3 into the original function, you get out a negative 2. So when you put a negative 2 into its inverse, you're back where you started. That's why the inverse of g of negative 2 is negative 3. I want you to go ahead and let's talk about these first ones, these next two. First, I'd like you to find g of negative 1. G of negative 1. Okay, g of negative 1 is just saying you've got your graph of g of x. What do we get out when we put in an x value of negative 1? So I go to negative 1 and I go up. Here's my point. This is the point negative 1 comma 2. G of negative 1 is that y output of 2. Now what I would like you to find is the inverse of g of 6. The inverse of g of 6. All right, now we'd actually already labeled this one on our paper because we had already done g of 1. If I went and I asked the question, what value input to g gives me an output of 6, the answer would be 1. So when I ask what would the inverse give me, if I put a 6 into the inverse, it would give me 1. It would give me what I would put into my original function to give me 1. This is asking the question, g of what value equals 6, and the answer is 1. And so if you start to understand that metaphor of switching x and y values, one really powerful thing we can do is we can graph inverse relationships. To graph an inverse relationship, we simply swap all of the xy coordinate pairs. Everything that was an x becomes the y. Everything that was a y becomes an x, and you just keep the pairs together. What you're going to see, so for example, 4 comma 2 on your old graph would become 2 comma 4 on your new graph. What you're going to see, and you'll see this when we finish this, is that this has the visual effect as if you drew a line. So you can see on this graph up here, there is a line that goes from the bottom right corner to the top left corner. It's a dashed red line. Finding the graphical inverse of a function is going to be like folding your line over that line y equals x. You're folding your function over that line y equals x. First though, if we just had to graph this, what I'm going to do is I'm going to just keep finding points. I'm going to find points to use to graph. So this is the point 1 comma 9. Keep looking for another one. Here's one. 0 comma 5. Again, I'm just looking for ones that are on whole number values. Negative 1 comma 1. Let's see. Negative 3 comma, oh sorry, that's negative 2. Negative 2 comma negative 3. And finally, negative 3 comma negative 7. To graph the inverse of this function, you simply swap each of these x and y values. So this becomes 9 comma 1. This becomes 5 comma 0. This becomes 1 comma negative 1. This becomes negative 3, negative 2. Because again, it's just if we graph the inverse, we're just graphing what the opposite would be. So the inverse, instead of a 1 going in and a 9 coming out, a 9 goes in, a 1 comes out. Instead of a 0 going in and a 5 coming out, a 5 goes in, a 0 comes out. I've got 1, negative 1, then I've got negative 3, negative 2, and then finally I've got negative 7, negative 3. And so if I graph this function, do better than that. Do better than that. All right, I'm going to take it real slow. Here we go. Still missed by a little bit. What I want you to really see visually is I want you to imagine folding your paper. Imagine folding your paper over that red line and see how the blue dotted original function would become the red dotted new function. That is what an inverse is going to look like visually. So if you were just like doing a quick multiple choice, you could maybe rely on that. But otherwise, what you would do is you would just carefully graph points to find the inverse. We'll do one more. Let's say we wanted to graph the inverse of this relationship. So we've got this what looks like a parabola, but opens over to the right there. And so I want you to just picture in your mind at first, what is this going to look like when I fold over this line, y equals x. So imagine it to yourself. Imagine folding it one way and then folding it the other. It's kind of hard to know exactly, but I think if I were to do a quick sketch, I think it's going to look something like that, right? I don't think I have it perfect, but if you imagine folding over that red line, it's going to look something like that purple graph. Let's see sort of exactly where it winds up. So again, you find some points. The bottom of the parabola, the vertex of the parabola is at -4, 6. So its inverse will be at 6, -4. Do that in a different color. So its inverse will be at 6, -4. Let's see where that is. 6, -4. Okay, so I was off by a bit, but you can imagine if that's the vertex of your parabola, if you wanted to just do a quick sketch, yeah, our graph is going to look something like that. Let's finish it out though. If I do another point, let's see, I've got -3. Ooh, okay, so our original one is not a function. That's why I used that word relationship. Because there are 2 outputs for every 1 input. So we've got -3, 7, and our inverse will be 7, -3. But we've also weirdly got -3, 5. Again, this is why I use the word relationship, not function, because we've got 2 outputs for 1 input. Remember, that means this is not a function. But graphing its inverse is still the same idea. So we've got 5, -3, and 7, -3. Let's do 2 more here. I've got 0, 4, and 0, 8. So I've got 0, 4, which will become 4, 0, and I've got 0, 8, which will become 8, 0. So if I graph these 2 points, 8, 0, 4, 0, here we go. So, way better now than my original guess would be, but the same idea. The same idea applies here, that we're flipping this over that line y equals x. So the final key point for today, to graph a relationship's inverse. An inverse function is one where all of the old inputs become the new outputs. All of the old outputs become the new inputs. Inputs and outputs are x and y. So we create a graph where all of the x-y pairs are swapped. Visually, it is like you flip over that diagonal line, the line y equals